Hello, children. I hope you're having a wonderful day today. Today we're going to be talking about how we find the volume generated by a solid of revolution using the washer method. The washer method is essentially what happens when we try to rotate something around a line and it creates a hole in the solid that we're revolving. Generally, this is going to happen because we're intersecting two graphs that do not lie flush along the line that we're trying to rotate around. So let's see what happens. Hopefully you've watched the Khan Academy videos. Again, he's a much better drawer than I am, so hopefully that gave you the concept of what we're trying to do here. Okay, so if rotating creates a hole in the solid, then we use the washer method. To find volume. So what you should have seen was that he developed for you the entire concept. So I'm just going to give you the equation here. The pi, of course, because we're finding the area of those disks from A to B of the radius function for the outer edge of the disk minus the radius function for the hole in the disk. And this is for when we're rotating around a horizontal line, like the x-axis. Okay, remember that we use capital R of x. This is for the outer radius. And lowercase r is what I'm going to use for the inner radius function. This one is what's creating the hole. And so this is the generalized equation that we would be using to find the volume. Remember that if you want to rotate around the y-axis, okay, it's just a very small change. We're still doing the integral from a to b, but now our function becomes r of y, which means we have to have an equation with y's in it, minus, of course, little r of y dy, and this is for when we're going around a vertical line. Like the y-axis. But it could be any vertical line, it doesn't have to be the y-axis. So the concept is the same. You take the area of the disk that creates the outer edge of the solid that you're revolving, you subtract the radius function for the hole that's being created, you take all of those little disks, which is pi r squared, and you stack them up and add them together, which is why we're taking the integral. Okay, so let's take a look at our first example. Our first example is that we want to find the volume created by y equals the square root of x and y equals x squared around the x-axis. See if I can squeeze that in there. Okay, so if we are going between two functions, okay, most of the time they're not going to give us the limits of integration. because when we go ahead and graph those two things, they're going to intersect and we're going to get an area between two curves that we are revolving to create our solid object. Okay, so first thing we have to do is we have to go ahead and get these functions graphed. So again, just quick plugging in some points. If you start graphing and you realize that your points are going too far out away from where you want to go, you can go back and do it again. One thing that I might recommend is that you go ahead and find the points of intersection first, so you know your limits of integration, and that way you can pick some points that will actually help you get a good picture of what you're looking at. So why don't we do that? Why don't we go ahead and find the intersection points first? Since we're going between two graphs, I know we're going to need to intersect these two graphs. So we set them equal to each other. Okay, and we're going to solve this. So let's see, let's go ahead and square both sides first. So that equals x to the fourth, right? Okay, and then we'll go ahead and move this over. And then we'll get, if we factor this, okay, and of course when we factor this is going to factor some more. So we need to go ahead and factor this cubic. Okay, so when we factor this, we're going to get x. This is going to factor into x minus 1 times x squared plus x plus 1. Okay, so our answers from this is equals 0, equals 1. This one doesn't factor anymore, and if you put it into the quadratic formula, it gives me non-real answers. So these are the only two intersection points. So I can see that I'm only going to be integrating from 0 to 1. So when I plug these numbers in, I want to make sure I pick some numbers between 0 and 1 so I can get a good picture of what these two graphs look like. Okay, so let's go ahead and do our first function. It's going to be our blue function. Y equals the square root of x. So if I plug in 0 for x, I get 0. Okay, if I plug in 1 for x, I get 1 for y. Okay, but I'm also going to pick a point somewhere here in the middle. So I'm going to plug in a half. What is the square root of a half? That's 0.7. Okay, and maybe I'll put in a fourth. Square root of 0.25 is 0.5. So that gives me a pretty good idea that this function kind of looks like this. And then we'll go ahead and we'll do this function. Okay, so if I plug in 0, of course, there we go, I get 0. If I plug in 1, I get 1. So this is the problem that y'all were having yesterday on some of the questions, was that you're only graphing 0 and 1, and then you think these functions are on top of each other. That's why it's good to get the intersection points first. Okay, so if I plug in half to this, so if I plug in a half, my answer is a fourth. If I plug in a fourth, my answer is a 16th, so I can see that this is a parabola, kind of looking like this. And so now I can clearly see the area that I'm trying to rotate around the x-axis. Okay, so this little piece up here we don't really need, so I can go ahead and get rid of this so I can see exactly what it is that I'm going to be rotating here. So essentially what's going to happen is that we are going to have it's going to reflect across, and we're going to get this coming over here, and all of these points are going to reflect, so they're going to be coming over here like this. And so you can see that this is kind of the shape that we're getting here. We're kind of getting our circles. They're going around like this. And this okay. So if we take a look at our circles that are here in the middle, which will give us a little better idea of what we're trying to do with our outer and our inner function. So we've got our circle going here. Okay, so hopefully, if you're looking at the circle, you can see that going to my outer function, which is the blue function right here, you can see that my blue function goes all the way to the x-axis, okay, but the hole in what we're rotating here is being generated by the pink function. So the values from the pink function to the x-axis are what we're going to be subtracting out. So when we set up our integral from 0 to 1, because those were our intersection points, we know we're going to multiply it by pi because we're doing the area of these disks. Our outer function that's creating the outside of the volume is the blue function, so that's the square root of x. Okay, squared, because my r function gets squared, minus the inner function, which is x squared, which has to be squared. And we're going around the x-axis, so that makes this a dx. And all my things are in terms of x. So all we have to do is go ahead and find this integral. So you can go ahead and pause the video and see if you can figure out that integral, and then I'll show you the answer. Okay, so hopefully you work that out, and you can see that when I've taken that antiderivative, I get this. When I evaluate from 0 to 1, I end up with an answer of 3 pi over 10. So I'm going to go ahead and stop there and post this, and then I will work another example in a separate video.